Okay, we're going to talk about limits and continuity for functions of two or more variables. And I think it's helpful to first review limits from 17A, first quarter calculus, because some of the concepts apply here, and we haven't seen that for a quarter, another quarter or two. Okay, so recall your first rule of limits. If you're doing the limit as x approaches 2 for x squared plus 1, is just plug the number in, right? You plug in, you get 5. And what that says, that graph is a parabola. And remember what that says, as x gets close to 2 from either side, your y value is just getting closer to 5. So your first rule of limits is to just plug the number in. Okay. Then we got into some more sophisticated limits where you try to plug in the number 2 in this case, and you end up getting 4 plus 2, 6 minus 6, which is 0, and 0 in the denominator. And so back when we were studying these, we spent a lot of time talking about 0 over 0 limits, which are indeterminate limits, meaning just knowing the value of the limit is 0 over 0, you can't determine what the limit is because it could actually equal a number. Okay? Remember that I put in quotes here because it's not really 0. You're not really dividing by 0 because x is not really 2. X is approaching 2. So in reality, we're dividing a small number by another small number. Okay. And how did we deal with this? Well, at the beginning of calculus in 17A, we did some factoring, right? You can do some algebra, was what I always tell students. And if you factor, you get the common factor of x minus 2 to cancel out. Plug in the 2, and you get a 5 for your answer. Remember, you can also do, later on in 17A, we learned about L'Hopital's rule. So you could definitely use L'Hopital's rule as well. Also want you to remember what that meant graphically. When you have a limit where you get a common factor canceling out like this, what is happening is at x equals 2, you have a hole in the graph. Once those factors of x minus 2 cancel out, the graph looks just like the graph of y equals x plus 3, but you're going to have a hole in the graph. And okay, as we also talk about continuity, this function would not be continuous at x equals 2. Why? Because f of 2 is undefined, right? There's no function value at x equals 2. Okay, my third example from 17a involves a piecewise function. We're looking at x squared when x is less than 2, less than or equal to 2, and the line x plus 1 when x is greater than 2. And if we're asked the limit as x approaches 2, what we have to remember to do is check out the one-sided limits. Okay, we need to see what the limit is as x gets close to 2 from the left and as x gets close to 2 from the right. Okay, graphically, you can already see this. I've already graphed the parabola and the line. But if you didn't have the graph, from the left of 2, you would know you're on the x squared function. So you just plug in the 2, you get 4. And you would plug into the line when x is approaching 2 from the positive side, and that would give you 3. Because the left and right-hand limits don't agree with each other, we say that the limit does not exist, which is another reason a function could not be continuous at a particular number. This function is defined at 2. Unlike the previous one, it is defined at 2, but if the limit doesn't exist at 2, then it's not continuous. All right, now back to 17C. If you get a limit, now we have x and y approaching a point, right? X is approaching 1, y is approaching 2 of some function, which we now know these functions graphically define surfaces, right? If it's a function of 2 variables. Okay, but your first rule should still be to just plug the number in. So I'm going to plug in 1 for x and 2 for y, and that gives me an answer of 6. Graphically, the way you could interpret this, the function z equals x squared plus y squared plus 1 is a paraboloid. We graphed that on one of the earlier videos. That's a paraboloid just shifted up 1 unit. And so graphically, you could interpret this as your x approaches 1 and your y approaches 2. So on the xy plane, you'd be at the point 1, 2. Up on the surface, your z value would be getting closer to 6. Okay. So that part's the same. Your first rule is still to plug it in. Okay. But, oh, sorry. Now, what if we get an indeterminate form? Here I have x and y approaching 3, 3. X squared minus y squared over x minus y. If I plug in 3, I'm going to get 0 on the top, 0 on the bottom. Now, what did we do when we had 0 over 0 before? We did some algebra, okay? And that's should be fairly obvious. The top factors as x plus y, x minus y, common factors cancel. You plug in 3 for x, 3 for y, and our limit is 6, okay? Let's go to our next one. Okay, so now I changed it a little bit. The denominator is now x squared plus y squared, and x and y are approaching 0 and 0. So clearly, if you plug in 0 and 0 for x and y, you're going to get 0 over 0. Our normal default would be to do some algebra, but okay, you hopefully realize that doesn't factor, right? X squared plus y squared it is what it is. It doesn't factor anymore. Now, remember our backup was to use L'Hopital's rule in 17a, but sad news, unfortunately, L'Hopital's rule only works in single variable calculus. So we can't apply L'Hopital's rule in this situation. So here's going to be our strategy. We're going to try to show that this limit doesn't exist. Okay, and the way we're going to show it, if you go back to our first example in 17a, one way to show a limit doesn't exist is if we can show that if we approach the point from 2 different directions, that we get 2 different answers. Now, one difference here from 17a is x and y is approaching 0, 0. Okay, in 17a, we only had x approaching a number, so we were only allowed to approach, if you're stuck on the x-axis, you can only approach an x value from either the right side or the left side. But if we have y to play around with as well, we get to approach 0, 0. We can approach that along any line or equation or graph that goes through 0, 0. This line, the x-axis, is y equals 0. That is, we call that a path. That's a path that passes through 0, 0. And x equals 0 also passes through 0, 0. So we're going to see what happens if we approach along those 2 paths. Okay, here's how it looks. So if we approach along y equals 0, what you do then is if y is 0, I can just replace y is equal to 0. So this limit is just x comma 0 approaching 0, 0. There's my function. Now, if y is 0, then there's nothing there, right? This would be 0, this would be 0. And so I'm left with just x squared over x squared, and now it's just a limit as x goes to 0. But these guys cancel out anyhow, right? So my limit's going to be 1. If I approach along x equals 0, now x is 0 and y is approaching 0. Now the 2x terms are gone, and I'm left with negative y squared over positive y squared, which cancels out to give me negative 1. So then, because we've approached 0, 0 along 2 different pathways and got 2 different answers, this limit does not exist. Okay. All right, let's look at our next one, number 7. We've got the limit xy approaching 0, 0 again, 4xy over x squared plus y squared. It's also a 0 over 0 limit, and algebra won't work. So here's the deal in 17c, actually for any multivariable calculus class. Unless we're told otherwise, we're going to have to assume that the limit doesn't exist. The truth is this, that there are lots of 0 over 0 limits that involve x and y, 2 variables, where the limit does actually exist, even when you can't do any algebra to cancel anything out. The problem is we would need to know that ahead of time. Otherwise, we might be trying to show that the limit doesn't exist, and we'll never get to the end of the problem. We'll never be able to figure out that the limit might actually exist. So usually when you get these types of problems, if they will imply or tell you that the limit doesn't exist, because then you know to show that the limit doesn't exist, we're going to try, okay, we'll call this the two pathway technique, where we approach 0, 0 along two different pathways that pass through 0, 0. Okay, so and here's why. There's an infinite number of pathways that approach 0, 0. I can try y equals 0, x equals 0, like we did on the previous problem, y equals x squared, y equals x cubed. Any equation you can think of that approaches 0, 0 is a legitimate path. So there's an infinite number of pathways that go through 0, 0. Now, what could conceivably happen is you could try 10 different paths and get the same answer for all of those paths. But all it would take is another path that you haven't thought about that gives you a different answer, and the limit would not exist. So because there's no way to test an infinite number of pathways, that's why we have to assume the limit doesn't exist and try to find two of them that give us two different answers. Because if the limit did exist and we tried 10 different pathways and got the same answer for all of them, we wouldn't know still, right? There might be a path out there that gives us a different answer. Okay. So let's get to it. So let's try, I usually start just to generate a baseline, just to get some answer here. I try either y equals 0, x equals 0. So let's start with y equaling 0. And if y is 0 and I plug that in, the numerator will be 0, the denominator will be x squared, and 0 over anything is going to be 0, right? 0 over x squared. Note, hopefully you can see this, if I tried letting x be 0, then I would have had 0 on the top and I would have had a y squared on the bottom, so that would have also given me 0. So my goal is to get a pathway, find a pathway that gives me an answer other than 0, different than 0. So now let's try y equals x, because that also passes through the origin. And if you plug in x for y, you're going to get 4x squared over 2x squared, which cancels out and gives you 2. So now that we have two different answers, we can now claim that the limit does not exist. Okay, I think I got a couple more examples. All right. So here's one. I've got limit as x, y approaches 0, 0. 8x squared y over x to the fourth plus 3y squared. That's going to give me 0 over 0 and no algebra that will sort that out. So I'm going to assume the limit doesn't exist and try to prove that I get two different answers along two different pathways. Starting with y equals 0, I get 0 if I plug it in for y, 0 down here, 0 over x to the fourth is equal to 0. And you can probably see that if you had let x be 0, you would have gotten the same answer. You would have gotten 0. So that's not going to help us. The next thing I usually try is like a line through the origin, like y equals x. If I plug in y equals x, however, I get 8x cubed on the top, x to the fourth plus 3x squared on the bottom. If you factor out an x squared from the bottom, that'll cancel out with 2 of your powers of x. And notice I still have an x on the top, and if I now let x go to 0, I'm going to end up with 0 over 3, which is still 0. And see, that's not helping. I'm trying to get something different than 0. So we need a different path. And usually what I find is that if you try y equals x and it doesn't help you, that means any line, y equals 2x, 3x, negative x, it's probably not going to help you as well. You're probably going to get 0 for that. So what do? Let's bump it up a notch. How about trying a parabola? Okay, because y equals x squared also passes through 0, 0. And if I plug in x squared for y, I get 8x to the fourth on the top. This becomes 3x to the fourth, which I can combine. I get 8x to the fourth over 4x to the fourth. Those cancel out, and I get 2. And so now I can claim, because 2 is different than the 0 I got before, that that limit doesn't exist. A question I get all the time is, how do you know what pathway to choose that's going to, get you something different than 0 perhaps? The one thing to think about that you might notice is when I plugged in x squared, notice it made the degree of the top and the bottom the same. So that's the secret. If you can look at the problem and try to figure out what you could substitute in for x or y and make the powers the same, that's a good path to choose. One final example, and this is kind of a cautionary thing here, you'll notice that many of the problems that you encounter where you have to choose 2 pathways to prove the limit doesn't exist always go through 0, 0. And so we kind of get used to picking the same paths, x equals 0, y equals 0, y equals x. But be careful. Okay, this particular limit gives me 0 over 0, and I can't do any algebra. But notice x and y are not approaching 0, 0. X is approaching 1 and y is approaching -1. So that means you can no longer choose the paths we were choosing before. You can't choose y equals 0 or x equals 0 because it doesn't go through 1, -1. What does go through there is the line y equals -1 and the line x equals 1. If I approach along x equals 1 and plug in 1 for x, I get 1 plus y over y plus 1, which is just 1. And if I approach along y equals -1, I get x minus 1 over -x plus 1. If you factor out the negative from the bottom, you'll see the x minus 1's cancel, and that leaves you with -1, which means the limit doesn't exist because we got 2 different answers, right? Okay, hopefully that helps. Yeah.